All right, so how you guys doing today? Good. Okay, perfect. So please remember we have an exam next week. So what I'm gonna do is I'm gonna try to finish most of the parts of chapter five. No, chapter six, and then I'll try to hold the review session from actually this Wednesday. So we're actually gonna have 3 review sessions, so it'll be even better. Okay. So yeah, but yeah, we'll try here. Okay. So, all right. So today we just briefly talked about the quantum numbers last time. Okay. There are 4 of them there. Okay. So the first one was the principal quantum number. Okay, this is n. This is denoted as n. Okay, we have angular momentum quantum numbers. We have the ML. We have the magnetic quantum number. And then the last one was for electron actually. So those are for the orbitals. This is electron. Magnetic spin. Okay. Electrons. Okay. So well, we're gonna talk about this one sometime today, but let's just focus on this one. Okay. So this n is principal quantum numbers. It actually indicates the energy level, or you can say the distance between your electrons, okay, and nucleus. Okay. So here's the thing: if you have an n number is really high, okay, that means you're going to have you can store the electrons around the nucleus and further away from the nucleus. So if you have a very strong and heavy elements that can actually store electron far away from there. So if this is the nucleus at the center, okay, neutrons and the protons, we're gonna use it for now Bose model. Okay, this is the Bose model. So you have maybe electrons were here, and this is the lowest possible energy level for this atom here. We call this a ground state, or the ground level. So like at the lowest possible level, at which is always n1. Okay, so n is equal to 1. This is the lowest possible energy level you can go down with the electrons, and this is nucleus. So there is no such a thing that is n is 0. This is impossible because obviously, if it really means the energy level, simply distance between your electrons and the nucleus, if the n is 0 means what? The electron should be in the nucleus, which is impossible, right? And also there's one more thing. So if you go higher and higher, it'll be n2, n3, n4, n5, and so on. So in that case, the weird thing here, it looks like an H though, right? It's N. So the weird thing about this one is when this atom, this element, got an energy in form of light or heat, they can be more energetic. So they can actually keep the electron in the high energy level. So if you're like a weak person, if you try to protect your money from others, you're gonna just try to protect your money like close to you, because you don't want anyone stealing your money. But if you're strong enough, you have a more ability, capacity to keep the more money a bit away from you, but still no one can steal the money from you because you're strong. Okay? So that means if you that become energetic, meaning this element has a lot of energy in form of light or heat, they'll be able to move this electron to high energy level. So they can either even put N2 or N3. Okay, does it make sense? Okay, so means if there's energy comes in, like maybe normally it's light or heat, and electrons can be at a higher energy state. It's excited state. So they go into the excited state. Means they're being excited by getting a lot of energy. So electrons goes the higher energy level, either 2 or 3 or 4, even higher. It depends on how much energy they got. Okay. So the funny thing is do you guys remember the quantized energy? Okay. Quantized energy. Okay. So this is the part we discussed about the particle-like nature of the electrons or the light photon here. So meaning there is an N1 here in this orbit here, which we're going to switch to the orbital next time, but for now, this is easier to look at. So this is an N1, and the electron, when it gets excited, gets a lot of energy. They can be stored in a higher energy level. They go to maybe 2 or 3. Let's do 3 there. But the electrons cannot be existed in between. So they can be only stay at either N1, N2, N3. So for example, if there is some space, maybe you can say N is equal to 1.5, okay? But when electron move to the higher energy level, they cannot be in this interval. So that means they have to do jump. So we call this quantum jump. So meaning, so electron moving not like this, they just do jump. So we call this quantum jump, but to be more realistically explained, it's teleporting. So once you have an electron here, and they're excited, they just disappear and appear on the 3 right away. Because you have a quantized energy. So they can travel through the energy level just passing through it now. There's a certain way electron can be existence, somewhere between is impossible. We couldn't find it. So this is for sure the evidence of what? The matter of the electron here is quantized. There's no between. So this is kind of a weird phenomenon. Isn't it weird though, right? It's kind of weird. So anyway, so when it happens to that, they excited there. So now you're sending the electron to the high energy level. But after some time, it's excited means they're unstable, okay? Because they've got a lot of energy. But to be stabilized, they can bring this electron back to ground state again, like N1 or even lower. It doesn't have to be always ground state, but maybe N2 from M3 or 1, you name it. So if they do it, they can be what? Stabilized again, but they can be stabilized by emitting the energy now outside. So once they get excited by getting energy from outside, right? Now they're gonna release the energy so they can be stabilized. So if you're really energetic, you feel like you have a lot of energy in your body, what you do? You do exercise, right? And when you do exercise, meaning you using a lot of your energy in your body, so you can be finally at calm down, because you don't have energy to move much. So when it does do that, what they normally do is they try to emit a light. So light is what? Form of energy. So they try to emit the light here, okay? And then we can actually calculate. Let's do this later a little bit, okay? You can actually calculate the amount of the energy by using one equation here, which is what we call, this is delta E, meaning change in energy, okay? It is equal to negative 2.18 times 10 to negative 18th joule, okay? And with the parenthesis, we're gonna have NF, 1 over NF minus 1 square, and N initial square. Okay, so for example, your electrons were in maybe N4, okay, N4. And now they try to come down, so they put this electron in the ground state, which is N1. Okay, so obviously to do that, they need to release the energy in form of light. Okay, we try to find out how much energy in this light right now. Okay, so this is the one which you can do. This is simply negative Planck constant times speed of light times Rydberg constant. So this is about 6.626 times 10 to the negative 34 times the 3 times 10 to 8 meter per second. And the Rydberg constant is the 1.097 times 10 to negative 7 per meter. Okay, so you see those cancel out. You just got this is joule per joule times second. So times second, the meter cancel. You only get the numbers in joule. This is what this number is. Okay, so this will be given. You don't have to memorize it, but this is what we're gonna use for calculating how much energy can be released from one electron moving from the high energy state to the lower. Okay, does it make sense, right? Good. Okay, perfect. This is actually quite easy now. Then, only thing you have to do is you have one electron in energy level 4 and 4, and now it's at 1, and then you just need to get this. This is the final state, right? This is the initial. So you just need to change this one to 1, 4. Okay? So if you do this one together, it would be 1 over 1. 1 squared is just 1, right? Minus 1 over 4 squared is what? 16. Okay? So 1 minus 1/16 is what? 15 or 15/16, right? Okay. And then, if you do multiply these two together, it's going to be what? Negative 2 or 4 times 10 to the negative 15. So this is the energy you can have in the light that generated from the one electron coming from the energy level 4 down to 1. Okay? Okay. Does it make sense? Okay. Okay, so let's try to do this one. Okay, so let's say we have an energy level 2, and now they're down to 1. There's 1 electron, we're in 2, and now down to ground state, and is equal to 1. Okay, so let's try to do the same. Okay, and what's the answer? What might be the total amount of the energy you can possibly have at max and the light if it's emitted from the electron coming down from the N2 to N1. Okay. It's not that bad. Okay, so it will be what? 1 point. Oh, you guys didn't. Oh, yeah. Go ahead. I'm sorry. It's 1.635. Am I right?
Yeah, you're right.
Okay. There you go. You got it, right? All right. So the let's do one more and we'll move on. Can you guys do N3 to N1? Okay. We'll do the same thing. Okay. So what you just need to do is what? Switch this one square. Here, okay, so now it will become 9, right? So 1 minus 1/9 will be 1. Okay. So just make sure you guys put the negative here, meaning what? It's being released from the system, right? Because they are now emitting the energy outside. That's why it's negative. This is they're releasing the energy in form of light. Okay, about 1 minute. You can try. Okay, so it'll be 1.9? 1.9, right? But yeah, make sure you guys just do this and then. All right, so can I move on? All right, so finally, let's talk about the quantum numbers. We just talked about the principal quantum number. Okay, so the next one is the angular momentum quantum number. So the angular momentum here, so this N stands for energy level, right? So how much of the area they can store the electron around the nucleus. So we'll determine the orbital size or something. But this one will determine the shape of orbitals. So once again, orbital means like a 3D imaginary 3D space where we think that we can find the electron by high chance. Okay, so this is not real, but this can be mathematically constructed, and this is the one that determines the shape of the orbiter here. So if your L is equal to 0, it means it's S orbital. If L is 1, that is the P orbital. If L is 2, it's the D orbital. Oh, let's actually make it with small letter. D orbital. And if L is 3, it's F orbital. Okay. So here's the thing. If that has a angular momentum of the how you can arrange the possibility of the finding electron in this 3D space. If you have a nothing in it, it means whenever you have 3D coordinates here, they shouldn't have any directional point where you can possibly find the electron by a higher chance. So that's why S orbital will become the spherical shape. When L is 0, there's no angular momentum you can apply to it. So this area we just what? Sphere. There's no preference on any directional point there. But when you have a 1, which will actually give us some momentum, so that will actually give us some directional position where you can find the electron. It looks like a dumbbell shape. It looks like this. So either they can align here or here or here, but that's what it looks like. And the D orbital over here is there are 2, so it actually looks like butterfly. Now they have a 2 dumbbell shape like kind of combined together because there are 2. So 3 is pretty much the same. You just need to add one more. It's like a flower. There's some weird shape, looks like this. Like a ring. This is the same as another, so this would be D. You have a double ring structure in the F orbital sometimes. It's 1, 2, 3. But just as what it really means is whenever you have some angular momentum in your orienting the finding probability of finding electron. This is kind of the 3D coordinates where you can see the probability of finding electrons. Okay? Yeah. So can I move on? Okay. So the next one is the magnetic quantum number. So magnetic quantum number is simply this one. Okay. Whenever you have an L number, which is 0, 1, 2, 3, it will determine the orientation of your orbital. So, like I said, if you have a dumbbell-shaped orbitals, it could be aligned with the x-axis or y-axis or z-axis. It depends on the magnetic quantum number. So, meaning, obviously, whenever you have an s orbital, which is a spherical shape, it shouldn't have any orientation, because however you put the sphere, it's just a sphere, right? There's no directional point there. So that's why your ML is just 1, which is what? 0. Because it's just sphere there. Okay? If you have like a p orbital, which is 1, only thing you have to do is whenever you see the integers on this L, your angular momentum number, just put the -1 and +1 on the side. And then count all the whole number, integers in between these two, negative and +1, including 0. So in this case, if your L is 1, for ML, for your orientation, you can have a 3 possibility. 3 possible ML number you can have. So this is a possible choice for your ML, which is your magnetic quantum number for p orbitals. Okay, so like I said, you can have just one, or you can lay on this one, or you can lay on this one, and so forth. There's 3 possibilities, but will be solely determined by ML. Okay, does it kind of make sense? So can you guys do this one maybe? This is 2, right? So it will be d orbital. So I'm gonna do the same. It will be -2 and +2, and I'm gonna count all the integers in between, including 0. So it will be -1, 0, and +1 will be all my possible choice for d orbital. So it will be 5. Okay. So s orbital only has one option, which is 0. For p orbital, you have 3 options, but for d you can have 5 options in here. This is how we define the ML, which is your magnetic quantum number. So either you're gonna have one choice among this possible scenario. Okay. So maybe if you have an f orbital, which is L is equal to 3, maybe you can do what? -3, perfect, +3, and you're gonna count. Perfect. All right. Next. Very good. There you go. So now you have a 7 choice there. So there are 7 possible ML from your L3, which is F orbital. So whenever you're doing this in the orbital diagram, we're gonna do this soon. But this is why the S orbital will have a 1 box, P orbital will have 3 boxes, D is 5, and the F orbital will have 7 boxes. Okay. So this is kind of something we can do. Okay. Can I move on? Okay. All right. So the last one, the magnetic spin is for electron. So whenever you put you can actually, there's some rule you can do is at max, you can only fill 2 electrons in one orbital. Subshell, orbital, like diagram or box there. So meaning if you have a P1, P2, or P3, there is only going to be 2 electrons can be occupied in each orbital. Okay, choice of the orbitals here. So if you have the one that going up is what we call upspin. Okay, we put a plus half for its magnetic spin number. So it's ms. Change this one to ms. And the other one is what we call downspin. It's just going down. So the upspin, downspin is the direction of the magnetic field direction vector. So you don't have to know for second one, but we scientists believe that the electron does not just stand, they just stand still in the orbital. They're always moving, and also they can rotate. So, are you guys taking physics? No, okay. So in physics, if you have some charged particle, or either you can have a positive charge or negative charge. Obviously, electron is what? Negative charge, right? So if anything that is charged with some, electropotential difference, if they move, so something charged molecule move, they generate the magnetic field. This is how we find the physics. We don't know why, but anything that is charged, if they move, rotating, or they move to the other place, they create the magnetic field in the space. Electrons in the orbit also rotating. So by that rotation, either they can rotate left to the right, right to the left. They can either put up or down spin. This is the direction of your electric field vector. Okay. So in this case, we only have two choices then: up spin and down spin. So down spin, we just put negative half for this one. So this is how you can feel the electrons in the orbital box, orbital diagram. So this is S orbital diagram. This is a P. This is a D. This is an F. Okay. Like I said, you have one choice, three choice, five choice, and the seven choice for this one, right? And then you can only fit two electrons in each box of the S, P, D, F orbital. So you can do one up spin and one down spin, and that's full now. Okay. P is the same. You just fill the electrons here, and then you can fill the down spin later. So at max in P orbital block, you can have only 6, 2 for each. Same. Okay. So it will be 10, it will be 14. Okay. So I don't know if you look at this one here, I feel the electrons, the up spin first, left to the right, and the down spin later. Once all the up spin fill in each, there's a reason why. I'm not going to talk now, probably next chapter after exam 2, but this is the last quantum number, magnetic spin. Okay. All right. So we're going to do this because this is really important for getting an electron configuration of elements, okay? Chemical elements, okay? So, for example, I'll tell you the several tricks now. You can try to copy me. Then you have some idea now. So you have a hydrogen, okay, here. You have a helium here. Okay. 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 And and then oops, I'm running out of space. Okay, so sorry, this is this one. So what I want you to know is this is the S block, okay, and this first and second column as well. So it's S block. Okay, just want you to remember this one. So look at the periodic table there. Okay, look at the periodic table. The first row, first period, and the first column and second column is S orbital block. S orbital block. Okay. And then, sorry for this this one, but you have except the first row, okay? The last 1, 2, 3, 4, 5, 6 is p block. So if you look at the periodic table, okay, you have the boron to the neon, right? That except the first one, except the helium, those last 6 columns except the helium is a p block. We have p block over here, okay? So p orbital block. And then you have some empty space here, and from here, you have some chunk of block there, right? It's the d orbital, d block. And if you go like a third and fourth row in between, there's a very small section that is for f orbital box. But to be honest, we're not going to do much of f orbital at all. So don't worry about this one too much today. But since it's s, d, and p. And then I want you to remember this one too. So each period has this stands for principal quantum number. So the first period is n1, second is n2, and the third row is 3 and 4 here. For this s column here. And just one more thing I want you to remember, and for the p2, okay? But just one more thing I want you to remember is you see this the scandium that has right next to the calcium. This part is on the n4 period, right? Even though it's in the n4 period, this block, D block, starts with 3, not 4. So this is yeah. If you're looking at this in the online, please look at the find the one in the website. But if you go there, you see the one right next to the calcium. It should be on the number 4, N4. But this one actually in 3D, not 4D. Okay? This is something I want you to remember. I'll tell you why maybe next chapter, but simply it's because of the 2n square rule. So we're gonna talk about this one later. But anyway, so does it make sense? So I'll give you one example here. So electron configuration form is simply you try to fill the electron one by one. So if you look at this one over here, this is first period is N1. So we're gonna name this one is the 1. This is S block, so it'll be 1s. Okay. For hydrogen only has 1 electron, right? Because 1 proton, so it'll be 1. Okay. So for hydrogen, this will be 1 because it's an S, 1 S because it's S block, and then there's only 1 hydrogen here. So 1 electron here, because we try to do it for the electron configuration. So the 1 electron here. So electron configuration form for hydrogen is 1s1. Okay? So that means for helium will be what? 1s2. Because you have a 1s1, 2. And then once again the s orbital will only have a 2 because there's only 1 orbital there. So the 2 is now it's full with just 2. Okay? So now for lithium here you have to do 1s2. So you always count the electrons from left to the right, top to bottom. And if you go down, left to the right, down, left to the right. Okay? So I'm going this way. So lithium, we're going to do 1, 2, 3. Okay? So we're going to do 1s, 1, 2. And then now is what? 2 in S. So we 2s1. So that means that lithium has an electron configuration form that is 1s2, 2s1. Just following these blocks in each period, except D will start with this 3, not 4. 1s, 1s1, 2, and 3. Makes sense, right? Can you guys do maybe? I'll show you the carbon here. Let's do carbon. So carbon is what? You have to count from here 1, 2, 3, 4, 5, 6. So I'm gonna do from here be 1, S2, and now you have a 2, S1, 2. Oh, sorry, S2. And now this is the P block, but on 2, so it'll be 2, P, 1, 2, 2. So electric configuration form for carbon will be 1s2, 2s2, 2p2. Okay? So what might be the nitrogen then? Will be what? 1s2, 2s2, 2p3. Makes sense, right? Okay? So just one more thing. Think about you doing this for the elements like, like an iron over here, or cobalt, or nickel, or copper, or zinc. It will be too long, right? It will be too long, right? So in that way, what you can possibly do is you can have an abbreviated form by using electric configuration form in the last column, which is noble gas. So for example, if you want to do the electric configuration form for sodium right here, okay? So then technically speaking, it will be 1s12, 2s12, 2p6, and what? 3s1. That would be the whole electric configuration form for sodium, right? But use the, okay, if you're doing this one here, go to right upper period and find the noble gas, that period, which is neon, right? So what you can do is the sodium is neon in the bracket, and then you can count just from here right away. Okay? Then you can do it this here with, which is now 3, right? 3s is s block, this is s block 1. That's it. So you don't have to do 1s2, 2s2, 2p6, 3s1, all that now. You can abbreviate in this the noble gas 1 in the bracket. Because the neon is what? Literally what it has all that already there. So if you just put it in the bracket, you only need to do 1s1, 3s1 for this one. Okay? Does it make sense? Okay. So can you guys do maybe mechanism? You can try. Either way, the long version or abbreviated version. We'll do this together. Yeah. And also probably sometime in Wednesday. But when we're done with that, this is the last part of the chapter 6. We'll start on the review from Wednesday. Okay.
How many questions will like this be on the test?
This one, not many, because we have 3 chapters to cover. We have about 25-ish, like a problem, right? So I mean, maybe 1 or 2, I guess. But I don't think it's yeah. Well, if you get used to it, you'll find there's some trick and we easy. Okay. So let's do this together. We try to do mechanism over here, and what you can do is 1s2, 1s block 1 2, 2s12, and this is still in 2, so 2p block 2p 1 2 3 4 5 6, so 2p6, and now you have down to n3, so it'll be 3s because it's s block, and now you have a 1 2, so it'll be 2. Okay, so this will be your electric configuration form for what mechanism. Okay, but you can also do this one is the same as what neon electric configuration form. So we're gonna put it in the much shorter version, which is easier. Like this. Okay. Makes sense, right? Yeah. Okay. So that's pretty much it. So I think we're done with the chapter 6 now. But I'll try to cover a little bit more, okay, on Wednesday anyway, so we can be 100% sure. And then we'll move on to the review from Wednesday. So we'll have a sort of like a 3 review at least. So we should be quite fully ready for the exam too. All right. So